TLDI last year, where I'm walking back from the conference venue with Ryan Newton, and he tells me, I have a problem. Let me tell you about it. See, Ryan works on distributed systems for computation. Like everyone will tell you that, CPUs aren't getting faster, so we need to, move our computation over onto multiple nodes so that we can deal with the larger size of data in question. And so the traditional way you'll go about doing this is you'll write a very optimized C++ program on each node, and then you'll use something like MPI to send messages between the nodes. And your system might run fast, and you'll write papers for systems conferences. But this is ICFP, and Ryan is a functional programmer. So we want to write like functional programs for our nodes, Haskell in our case, because there are a lot of benefits to be had. Type safety, EDSLs, memory safety. I don't think I need to harp on the benefits of writing Haskell in front of this audience. But instead, I should talk about the downsides of trying to use high-level languages that have memory management. And the big downside that you see when you're writing programs like this in Haskell and other languages is the cost of serialization and deserialization. You see, when you're writing a program in C++, you often are very careful about how you lay things out in memory. And you'll arrange for your data structures, even if they're pointer data structures, to all live contiguously in some arena or region that you allocate. And so when it comes time for you to send this data to another node on your network, well, the representation that you're going to send on the wire is exactly the same as the representation that you had in memory. So you just, blast it out, and things are fast. But in Haskell and another garbage collection language, you'll have, some sort of pointer data structure. It'll be splattered all about the heap. And then, the CPU has to work really hard to get your data into the serialized format that you can actually send over the network. This is a problem. So Ryan asked me, it'd be really great if there was a compact form for Haskell data types that I could easily send over the network and, save on all my serialization costs. And I said, that's impossible. You'd have to rewrite GHC to know about the new compact forms of the data types that you want to send. And I guess we could write another compiler, but it wouldn't be GHC anymore. So fast forward to Gothenburg for ICFP last year. I'm sitting in the Haskell Implementers Workshop, and Patrick Meyer has the exact same claim. He says, I'd really like a way to talk about data structures in Haskell that are already evaluated, that are in some sort of normal form. And I think that, something like that could reduce garbage collection and serialization overheads. So I start thinking about this a little more. See, the problem is, we want some sort of compact representation of in-memory data that's amenable to being sent over the network. But we don't want to have to rewrite all of our compilers to do it. We want to reuse our code for manipulating pointer data structures. And so the insight of our paper really is very simple. It's that let's not try to be clever with the data representation. Let's just say that the memory that is associated with the data structure we want to send over the network should simply be contiguous. And if it is contiguous, then we can get the things we want. So, on the airport, Ryan and I draw up a plan for our paper. And here's the plan. The plan is that we are going to make the in-memory representation of data structures in our program the same as our network representation. How are we going to do this? We're going to divide the heap into a region per data structure and make sure that the data is laid out in contiguous segments in these regions. And then we'll enforce some invariants on the data structures which are sort of reasonable for network formats, namely that they have no outbound pointers and that they are in normal form and have no mutable pointers. And this, it turns out, is enough to get the benefits you want. But let me talk about this in more detail. So in the traditional model, you're going to do some computations, and these computations are going to result in data structures that are throughout your heap. So in our model, we would like you to say, OK, now I'd like to send my data over the network. So you're going to compact it into some contiguous region that then I can send directly over the network. But one of the keys is this compact region is still in the same format as a normal data structure in your program. So you can manipulate it the same way. You can, for example, create a new data structure, which is shared with the old data structure, and amortize the cost of actually serializing the data so that you can send an update to your data structure in less time than the entire region you would have needed. So we're going to use an old trick for partitioning our heap. We're just going to say that our heap is divided into 4 kilobyte blocks, and we use a technique called the block structured heap, which lets us efficiently do this division while supporting larger block sizes for large objects. And we are going to give you an API that looks something like this. We're going to define a type of compact pointers. These are pointers which point into your compact region. So if I have compact int, that is a pointer into an integer that's in a compact region. I'll say that I can create compact regions. These return a dummy pointer that points to the region but doesn't say anything. And I'm going to say that I can append data into the region. So this says, given a compact pointer to the region that I want to append into, and the object that I want to append into the region, I can get back a pointer to the newly appended data structure which has been copied into the region. And finally, if I have a compact pointer, I can, in constant time, get out a normal pointer which I can then manipulate with my normal Haskell code. Here's an example. So here we create a new compact region using the new combinator. So we have a pointer to this, which doesn't point to anything in particular, just to the region. And now let's say I have some data type X, which I would like to send over the network. So X might be associated with some computation. So I'll need to first, when I want to append it, evaluate it into some actual data. Then I will copy the data into the region and get back a new pointer R, which points to the copy of the data in the region. Now, suppose that I do some more operations and I build a new part of the data structure, say Y, which shares some of the original data with this region. Then I can say, oh, please append this new data to the region as well. And now we will have just the extra part, only the new part of the data structure that wasn't shared, that was shared with the old region, data structure in the region, also copied. So the invariants for the network format we want are that there are, one, no outbound pointers in our region. Any data in the region should point to data that is also in the region. Because if you send some data and it points to something random, well, what is that supposed to be? That's not useful when I'm sending data over the network. And the other invariant we have in the network format is that all objects should be in normal form. That is to say, they are fully evaluated. Because we're not interested in solving the problem of transmitting thunks of computation, which maybe I want to have another node compute. We're just interested in transmitting data. So if I want to, let me say a little more about how we append data to our region, which will preserve these invariants. So we use an algorithm that should be very reminiscent to those of you who have used garbage collectors. It's essentially the algorithm for doing copying garbage collection. So when I have an object, first I copy it to the destination heap. And for each pointer field, I simply recursively process the object. I can eliminate the recursion by simply using the set of objects that I've copied in as my queue of things that I need to process in order to do the copy. And so when I copy to the destination, I want to make sure there's no mutable data. And when I'm copying these objects, I want to make sure they're in normal form first. So I'll first evaluate them before I go. And the compactable type class is just a way of saying, at the type level, that these are the restrictions I want on the data in question. So, what about garbage collection? So there's a big problem, which is that when you run the garbage collector, this is going to blow apart all of the contiguous data that you had previously. Let me explain with a more developed example. So imagine that I have two already compact data structures. One of them is a linked list from 1 to 3, and the other is a linked list from A to C. And I'm about to do copying garbage collection on them. So with the first thing I'm going to do is I'm going to evacuate all of the roots from the linked list into the to the to space, which is going to be the new region that I have. So I copy 1 and I copy A because both of them were roots. And then as I go along, I'm going to copy the pointers that are pointed to by 1 into the 2 space, then the pointer that is pointed to by A, the pointer by B, 3, and C. And now you can see that I've blown apart the contiguity of my representation when I ran garbage collection on my data structures. This is no good. So the answer to this problem is that we don't garbage collect it. Remember that in the invariance I stated for our region, there are no outgoing pointers from data that lives in a compact region. So when I realize that I am going into a compact region, I can say, oh, there's no need to trace this because there are no pointers, which means that there is no live data that could have been pointed to by the data in this region. Okay, but this is a paper about making things fast. So how fast is it? So the sort of flippant response is that it's infinitely faster because we don't have to do any serialization at all. This graphic is from Cap and Proto, which is a library in C++, which does something very similar to us, but in a manually memory managed language. But let's be a little more fair to our benchmark, because in the description I gave for the algorithm, we do have to copy the data in order to ensure that it is actually in contiguous form. So in this plot, it's a log scale, so I apologize. We have a comparison between compact normal forms, which have been normalized to 1, and the serial and binary serializer libraries in Haskell. There's also a Java comparison, but it's not a great one because we use the default serializer. So what do we have going on here? Well, we see that with very small data structures, the constant factors of setting up regions on our heap sort of dominate. So we don't do as well as serial or binary. But as the size gets larger, serialization really starts taking its toll, and we start seeing factor of 2 speed up. Now, the big jump you see at the breakpoint between once we're getting to a large enough size is due to garbage collection effects. Because now, when serial and binary are processing, they generate a lot of garbage in the process, and so the garbage collector takes a lot longer. But remember, the data in our compact regions doesn't need to be garbage collected, so we start saving a lot in that case. Another question you might have is, Edward, it's all very nice that you're sending the same representation of data over the network, but this is really stupid because, memory layout for data structures is a lot different from network data structures. Memory will be larger. I might want to pinch the bytes that I send over the network. And we did some measurements in our paper to sort of characterize what the difference between the in-memory representation size and sort of network representation size are. And so you can see with a binary tree, the binary tree was the benchmark I showed in the previous slide. With the binary tree, we see that there's a 4 times space blowup when you compare to binary or serial. More modest blowup with Java, but it's still larger. And so the observation we made was that actually, it doesn't really matter because when you have a sufficiently, large network bandwidth, the cost of actually sending this extra data is sort of, insignificant compared to the time that it takes to serialize. On a 10 gigabit Ethernet network, it'll only take you 0.2 extra seconds to send the data, whereas, serialization is taking you 7 seconds. So there's really benefits to be had. And one final benefit of setting up data this way is that now we have data in a contiguous region, we can directly RDMA it out to other nodes. So this experiment shows us when we are using a zero-copy RDMA communicating between nodes to transmit data, and you can see that there's an order of magnitude improvement. Sorry, the graph is also in log scale. So there are some other things in the paper that I haven't talked about here. For one, when you send data over the network in this way, you have to make sure that pointers are still going to be valid, because if you move the data to another address, then you have to fix up the pointers. But with 64-bit machines, you don't have this problem because you can just ensure that the memory regions are just disjoint between the nodes. And so, at the end of the day, this is a very simple paper. If you have a block structured heap so that you can easily create regions of your heap which are containing separate data structures, and if you only put immutable data structures in them, then with minor garbage collection modifications, you can get compact normal forms, which let you efficiently send data over the network while avoiding garbage collection overhead when they are in your program. Thank you very much.
Yeah, this is really cool work. I especially like how you managed to get the network format completely coherent with what you need at runtime. So you're completely saving the deserialization overhead. However, of course, it comes at some price. Namely, I think you mentioned the data duplication a little bit when you were talking about the size. But what happens if you have a large number of data structures that you would like to be compacted in your way, but they all happen to share that one big data structure immutable that is anyway already evaluated in the heap? Will that be duplicated n times, with n being the number of references?
So it depends on how you set up the compact region. So if you indeed give a different compact region to each of the little data structures that is pointing to the large data structure, then yes, you will end up with n copies. However, another thing you can do is you can simply have multiple pointers into the same compact region, so that you have the large data structure, your little data structures on the side, and then you simply send pointers to the same region, so you don't send any new data.
You need to have like a link between different compact regions then, of course?
No, there's no link between different compact regions. You just have a single region, but multiple pointers into it.
Yeah. Depends how large your region and that object is. Yeah, sure, understand.
So the argument that you presented for having a compact region was, and for having everything contiguous, was that before it was being sent, you could actually work with the data locally, then it could be sent without having performance that. If you are stopping garbage collection the second you enter into one of these compact regions, don't you have the possibility of making a large portion of the compact region become garbage and then ship the garbage back and forth across the network multiple times?
Let me say two things, and maybe it'll answer your question. One is that because we don't trace inside compact regions, if parts of objects in the compact region become dead, then yes, you will be wasting that space. One way to work around that is to sort of recompact the region occasionally, which is basically doing a copy and garbage collection, which will get rid of the garbage. The second answer to your question is if you are putting something in a compact region, you probably want to send it at some soon point. So, you'd hope that you'd avoid sending garbage over the network unnecessarily. I don't know if that answers your question.
So since, as you point out, append is a lot like a tracing GC, I wonder, could you make the GC do the append for you? Say, have a function that's like, please GC do this append in the future, and then you get a thunk back, and when you evaluate that thunk, either the GC has happened and done it for you, or you are forced to do it yourself.
It's a really great question. So the biggest problem we encountered when we tried to do this, and if someone has a solution, we'd be quite interested, is that when you are doing general purpose garbage collection, you may decide that some substructure of the part of the data structure that you wanted to compact is already reachable before you started compacting that part. So what will happen is that part will be garbage collected to the normal heap, and then later you will come and discover a forwarding pointer to the wrong data to the wrong area, and you'll have to copy it again. But we think that that could be a very useful optimization. It could also be useful when you decide that the data is dead by the time you get to garbage collection, so you don't bother compacting it.
Apologies if you already told us this and I completely missed it, but so has this landed in mainland GHC, or when will it?
That's a good question. So it is not currently in mainland GHC, although you can download the GHC distribution we modified and play around with it. we have hopes to mainline it. But there's some, so like the garbage collection aspect of this work, I think, could be independently useful to many Haskell programmers. The part where we're sending data over the network, well, that's a more specialized use case. You know, you need to set up your environment for, you know, when you're interested in that sort of case. So it's harder to make a case for mainlining it in that case.
I think many people would like it, but we should make the case.
Hi. So what happens when the blocks overflow, and do you also support block merging if you want to send more than a page size?
Great question. So something that I hid under the covers in the API description was I just said, oh, a new block. But you want to first specify what you think, how big you think the data structure in the block is going to be. Now, because a block structured heap lets you just make lots of blocks, we do support chaining blocks together. So if you overflow, you simply start writing into another block. And if your blocks are big enough, then it doesn't matter too much that you have a little bit of discontiguity. Yes, and that is stored in the metadata that, you know, we already. Yes, but logically they're all part of the same region. So you only ever send complete regions, if that's.
Have you thought about how you could apply this to maybe memory mapping files, and then all of a sudden you have some
it's a great use case, and I think we have a little evaluation on that in our paper.
Cool.
All right, let's thank the speaker.